the paper is titled Enabling Lightweight Transactions with Precision Time. So this uses PTP timestamping and constructs a key value data store and then does optimistic concurrency control on top of that. And it uses pretty standard ways of doing all of these. You would do it the same way. You would use OCC, but I think the paper is interesting in that it provides the contribution of what might be the gains we can get from that using precision time stamping for key value stores and then building optimistic concurrency control-based transactions on these key value stores. Okay, so again, appeared in ASPLOS 2017. Here's the link to reach to the paper. So there are two systems that the paper talks about. Semel is durable multiversion read optimized key value store. On top of this, they built Milana, a distributed transactional system that uses OCC over Semel. And both of them are, again, they use pretty standard way of doing things. But the two things that is described in the paper is one, use of precision time. The second, for building Semel on top of SSDs, they have a efficient way of changing the FTL, the translation map, translation layer at STD, so that they do multiversion writing, multiversioning in a more efficient way. So that's the paper. Okay. Okay, so what do we gain? I will talk about three high-level contributions of the paper, three things that the paper puts at stake in, and then I will go on to describe Semel and then the Milana. Well, I like to learn about what the names mean, but the paper did not have any clue about what Semel or Milana meant. If somebody knows, let me know. I tried to do a Google search, but I couldn't figure out a good, relevant naming story for the Semel and Milana. And I don't even know if I'm pronouncing them well. Okay. The first contribution is to move ordering of the critical path. So we have seen this idea in the paper that we discussed last week as well. What was that paper? It mentioned the Tapir paper and said that, yeah, we use a similar idea of unordered replication, but then we decide to order on top of that. Oh my God, I'm so old. What was that paper?
It was exploding commutativity for practical fast replication.
Yes. Okay, got it. The Osterhout paper from the NSDI, yes. In terms of a primary backup system, yeah, okay. So this is a similar idea. It says that, well, let's replicate without worrying about ordering, but the ordering here is taken care of by the precision timestamping. So they are going to use the total order that the precision timestamping provides. Of course, you can get a total order on other timestamping methods, but as the evaluation shows, the epsilon that you can get in ordering makes a big difference, and PTP epsilon is much smaller than the NTP epsilon, so you get a big gain in terms of reducing the abortion rates in OCC transactions, right? I mean,
epsilon is time uncertainty, right? The time skew.
Yes, times go. I mean, if you use something like logical clocks, etc., well, there is a problem there because you need to know everybody's logical timestamps to be able to do a total order. Otherwise, your total order is not very meaningful and you may not get linearizability. So it's the clocks give you a good total order that can correspond to that, and the lower the epsilon, the better. So that's the idea. The first contribution, by just using PTP timestamps, we are just doing the replication first and then ordering we get for free from the timestamps. Of course, this depends on epsilon. In the evaluation, I'm going to show that if the epsilon is smaller than, if the epsilon is big, basically you block the other client to write, even though the other write may have been finished. So this all depends on the precision of the timestamp. So this says that in recent years, we see PTP deployed more in data centers. So we are going to make use of that and show what it buys us in terms of key value store implementation in a pretty straightforward manner. Okay, so that's one. The second is on top of this Semel that uses PTP, timestamp key value store. They build optimistic concurrency control. They use optimistic concurrency control to support asset transactions. And this is the Milana system. So each transaction executes on a single client. That is an application server. They assume that these clients are not any client, but generally a well-known set of application servers. The client issues read-write requests to Semel storage servers, assigns PTP timestamps for start and end of transactions, and then the clients themselves also act as the coordinators to commit or abort the transactions, And commit or abort is via optimistic concurrency control and two-phase commit. They say that optimistic concurrency control is much better than two-phase locking because we can get more throughput and better latency. There wasn't comparison with two-phase locking. No, in the evaluation there wasn't a comparison with two-phase locking, but yeah, they just say that we use optimistic concurrency control. And well, the reason for optimistic concurrency control is also that comes in the next two contributions. This is a multiversion key value store, multiversion key value store. The timestamps give the versioning, and as we mentioned, they use SSDs, and they change the flash translation layer FTL so that they can have the multiversion storage more efficiently in terms of instead of a two-layer translation, they modify the FTL so that this multiversioning is done in one layer, and they say that this brings them a lot of efficiency, and especially the efficiency in terms of read-only transactions. The efficiency in terms of read-only transactions comes thanks to this PTP timestamps. Yeah, we will talk about this when we go to the Milana section, but what happens is Semel is a primary backup replication. It uses primary backup replication to build the key value store. The it can allow read-only transactions to be validated locally at the clients. So these clients interact with the key value systems, also cache some versions of the nodes themselves, but they can do the read-only transactions themselves without doing the commits on the primaries. For write validation, it's done with the primaries, but again, just using the primaries also save us some round trips. So that's what the paper talks about. But again, these are pretty straightforward optimizations when you are building a store. But the lessons here are, well, if you use PTP, how much we save in terms of latency and throughput. The paper shows that I would be happier if this was a real implementation, but looks like they use an emulation of the SSD layer and the results are achieved through that rather than a real deployment of SSDs and hardware. Yeah. Okay, any questions so far? Okay, I'll quickly go through then the Semel and Milana systems. Semel is this multi-version key value store. It's implemented over SSDs. SSDs normally require 2 mapping steps, key to logical block address and then to physical block number and page, but they modified the translation layer to collapse this 2-step translation into a single translation. So this is done in 1 step. This figure shows some example of how this is done. So the flash, we keep a log, but we also maintain, thanks to the lookup table, multiversion support, multiversion access to clients if they are interested in that. And as I mentioned, and as we are going to see soon at Milana, this especially helps for the read-only transactions, because you can have a read-only transaction that's serializable, not necessarily linearizable at the client side if the read-only transaction comes from a consistent snapshot. Okay. And this is the point about the lightweight inconsistent replication. Semel uses primary backup replication with a designated primary for each shard. It exploits PTP to relax the ordering requirement and commit each update as soon as majority of replicas acknowledge it. So there is no attempt at ordering the request. Rather, the requests are sent to primary. The primary replicates it to shard. As soon as the majority replicates it, it's acknowledged back. The primary does not try to order the request in terms of an ordering constraint, basically. Which one did I get earlier? Was this acknowledged later than this one? No. When it is acknowledged, it's sent to the client so that the client sees the acknowledgement. Later, for transactions, etc., we are going to use the timestamps that's put by PTP to order them. Yeah, so this is what the paper says. Since the replicated Semel operations are timestamped writes to independent versions of independent data items, there is no need to maintain ordering. The ordering is explicit in the version timestamps, which come from PTP, which are recovered along with the data. So the PTP, the precision time, actually provides a global reference that all the clients or all the nodes in the system agrees. So there is no explicit attempt at ordering. The server execute reads on the named version and reject the writes with timestamps older than current version, guaranteeing at most one semantics. So to explain the second part, if a client replaces a completed request after the server discards its version, a simple timestamp comparison blocks it from overwriting an earlier request on the same object. The client receives a rejection for the retransmitted request. Atmos 1 semantics is preserved. So we are going to see that there is also garbage collection going on to avoid wasting flash. Semel tries to balance flash remapping costs with the desire to provide historical versions within a certain window size. For example, keep all versions that are less than 5 seconds old. This is done by using some watermarking. Each client periodically broadcasts the timestamp of its last acknowledged operation to all storage servers. And the minimum of these timestamps is the watermark in Semel, so they can garbage collect the writes or the updates before that, not to waste too much storage at the flash level, and not to increase the remapping cost. Okay. I mean, this lets me think that the clients are a small number of clients that are part of the system pretty much, right? Okay, any questions so far? This was Semel. Now we are moving on to Milana. Okay. So Milana uses OCC. It builds on Semel. They say that OCC enhances concurrency relative to two-phase locking. That OCC is not prone to two-phase lockings, blocking, and deadlocks. Well, it makes sense. If you use PTP, it makes sense to use OCC to get more concurrency and avoid problems with two-phase locking coordination, because you get some coordination from the PTP timestamps already, sort of for free. But there wasn't a comparison with two-phase locking kind of protocol in the evaluation. Okay, OCC systems validate each transaction T before commit by comparing T's timestamp read-write accesses to those of other transactions to identify any access conflicts that violate a serializable ordering. Conflicting transactions are aborted and then restarted at the client. So the client is doing the transaction. The client gets a success from primaries. If one of the primaries says no go, the client aborts the transaction. So this is how 2PC write validation works. Okay, the client begins the transaction. It reads the items that it needs to read. Read A, read B. So here, this rec1 has the primary of the key A. So it reads from the primary. Primary has the acknowledged version, best version. Then it stages the write at its location by using write ABC, and then it starts the two-phase commit protocol. Okay, phase one is prepare. It sends this to the primaries of the corresponding data items. Here, since these three data items A, B, C, the primaries reside on each of the recs, one on rec 1, one on rec 2, one on rec 3 is sent to them. Then the primaries talk to the replicas. The replicas are always in the other two recs. When the primaries get this, the primaries also have an algorithm to check if there wasn't another transaction, there wasn't another write that touched these things. Otherwise, the primary sends abort. Okay, and one abort from any primary in phase two is automatic abort. The commit comes when everybody commits, but for that, the primaries talk to the secondaries. When they get the majority, okay, majority say that the primary doesn't see any violation using this algorithm one validation, it's valid, and the majority replicas store it, then the primary sends, okay, success, right, prepared. when the client gets all the prepared at phase 2, it makes a decision. If one of them is an abort, it contacts all of them to abort. If all of them are commit, it contacts all of them to tell the commit and get the commit things. And this is the 2PC write validation. This is nothing new, right? This is standard OCC on top. This is standard OCC transaction validation. Okay. I mean, algorithm 1 that the primary check is also the standard things that you expect. Did anybody else touch the key? Is this the valid version to use? Based on so when the client did this reads A and B, did A and B change after that? If it changed, then we cannot accept this transaction because it is based on old stale values. And what happens then? Well, the client needs to abort and retry. Of course, the problem with OCC is if there's conflict rates increase, you are in trouble. But the paper, again, hearkening to the first part, says that since PTP gives us very fine granularity, very precision timestamps, this helps reduce the conflict rate a little. And it also depends on the workload a lot, obviously. So for given workloads, this is reasonable, and this is a simple way of doing things. But again, I think I would have liked to see a comparison with two-phase locking. Obviously, since they use PTP, they wanted to use OCC, which comes because the ordering comes for free from the timestamps. But yeah, I wanted to see if the comparison and what are the advantages. If there are disadvantages, it talks about disadvantages of 2PL, but if there would be any advantages from 2PL, especially for high conflict rate workloads. Yeah, so I think I covered this, so I will go over this quickly. This is the interesting part. This was the fourth contribution that I mentioned. Milana supports snapshot reads and local validation. So Milana satisfies a transactions reads for a key by returning a version that is current as of the transactions TS begin, even if a writer has written a new version of K with a later timestamp. They say that this reduces false conflicts and improves concurrency and throughput because it's okay for a read-only transaction to read from the past, provided that that's a serializable past, provided that all the items that this read-only transaction reads belongs to consistent snapshot. In other words, if the read-only transaction has ABC, if we give a consistent snapshot of ABC, meaning that the version that we read for B, the version that A did not happen from it, before it. Or if the version for A is 1, the version of B, version 2 of A did not happen before version of B. Does this make sense? Then they say that this ABC belongs to a consistent snapshot. A would have happened before B if B returned the version 1 for A. Then version 2 for A happens, and then version of B happens. Then this would be happened before because we should have returned version 2 for A to be consistent for this version of B. Sort of like a consistent snapshot idea in terms of versions there. Okay, does this make sense?
Do clients know they read from the past?
Do clients know they read from the past? Is that the question?
Yeah.
I don't know. I don't think the clients matter. So these read-only transactions are not, they do not necessarily provide external consistency. They provide serializability, right? So this local validation procedure, it gives serializable transaction ordering, but you might be reading from the past. So this does not necessarily provide external consistency. They say that Milana provides both serializability and external consistency for read-write transactions, which validate on the servers. But read-only transactions, let's go back to this, they don't go to two-phase commit because they don't update the state. There is no staging off here. They can just read the from the primaries, and this could be slightly stale as long as they are consistent. They don't care. And this is end of transaction for the read-only transaction. And this is called local validation because we don't use phase 1, phase 2 for validation with the primaries. Okay, let's, so local validation for read-only transactions. Milana servers return sufficient version information to enable a client to perform local validation for read-only transactions. Local validation allows a read-only transaction T to commit if and only if the values in T's read set are from a consistent snapshot. And this is defined as follows. Each value for a K key in T's read set is the youngest committed version of key with timestamp less than or equal to TS begin. So the most recent committed version before TS begin. And no, there could be a write update after that, but we don't care. We just take the TS begin as the thing to return. And they, even if there is an update, as we said, to improve the throughput, the primaries return the most recent before the TS begin. And the second condition is no key in the read set has a prepared version with timestamp less than or equal to TS begin, meaning that there could be a prepared version after TS begin, but there shouldn't be a prepared version in progress before TS begin. Then this would be a consistent one. So this takes care of the stuff I mentioned about A has two versions, V1 and V2. But if we send V1, then V2 happens, then B's version happens. This is not a consistent snapshot. So this is taken care of by these two rules, saying that, well, A shouldn't have had version 2 prepare before TS begin. And that sort of makes sure the consistent snapshot. Then the client just uses this, and this is read-only transaction validation local at the client. Any questions? Okay, so, okay, fault tolerance. If the primary of a participant shard fails, then all the transactions are blocked until we select the new primary and resume operations with the new primary. The new primary would be known to the things. The paper does not discuss about the configuration service that keeps this primary and backup configurations and that does this reconfiguration if a primary fails. But what the paper says is that, well, as long as there is majority of replicas available, the configuration service can take care of things and select a new primary, and then we can keep going. So there isn't much of fault tolerance discussion, and there isn't evaluations with fault tolerance in the evaluation section. This is related to other OCC transaction systems, including Tor, which was, I think, like 25, 30 years ago from Barbara Liskow's group. Barbara Liskow started the first research basically saying that, well, we can use this synchronized clocks for timestamping and for some kind of coordination and OCC work. It was used for Tor. Then they compare with sentiment, and they compare in English with Tapper a lot in several places, in introduction, in a middle section, and later in a related work. They say that Tapper was designed for geo-replicated system, whereas we focus on inside a single data center. So our design choices reflects that. Tapper basically enables any node to become a primary, but we use a primary backup system, and this choice is reasonable for a data center because we we can go to the primary pretty low latency inside the data center, and we gain from using the primary because we don't need to talk to all replicas in the shard. We can get the write version from the primary, we can get the read version from the primary, so we benefit from this design choice inside the data center. Okay, and they say that since cross data center latency is high, Tapper was okay using NTP time synchronization, but inside the data center, NTP is too rough granularity and leads to a lot of abort with OCC, and by using PTP, we can achieve 43% lower transaction abort rates compared to NTP. Okay. Yeah, so evaluation talks about these things. Semel achieves 20 to 50% higher IOPS than a traditional separate version flash management approach. So reducing that, changing the FTL help. Again, these are taken from kind of an emulated SSD thing, not implemented on real SSDs in terms of this FTL and so on. They use the Retrivis benchmark, and they say that the client local validation of read-only transactions yields a 35% reduction in latency and 55% increase in transaction throughput for the read-heavy workloads. So this is figure 6 shows that multiversion reduces the abort rates. So MFTL is with the multiversion case, and you can see they have much lower abort rate than the SFTL single version ones, because your risk could be from earlier versions as long as for the read-only transactions, this is good enough. And if there is actual conflict, that will be detected for the write transactions. If there is actual conflict, that will be detected at the 2PC, and that would be aborted based on that. But optimistically, you should be okay. So the multiversion helps us with transaction abort rate. That's what the figure shows. Second thing is PTP reduces abort rates compared to NTP. So they have these PTP versus NTP for DRAM, multiversion, FTL, and we can see improved things. This is because the NTP in their evaluation, they found that it has average skew of 1.5 milliseconds. That's pretty good for NTP. In general, NTP can have more, but this is inside a data center. They run the experiments for 15 minutes, also enabling the NTP to stabilize. But PTP has average skew of 53 microseconds, and that's awesome. That's like awesome average skew, because, well, I guess these are sort of in the same LAN, belonging to the same routers, and PTP works well in cluster, because the big thing with time synchronization protocols is the non-deterministic delays that comes from routers, but with PTP, basically with well, the server is inside the same local area network, you can reduce them a lot and get to this microsecond level synchronization. And, you know, wireless clock synchronization is even better, because, you know, there is a time of flight for wireless signal, but you can pretty much calculate that. That's not non-deterministic for GPS synchronization, for example. If you know the distance, you can calculate that precisely the time of flight by using the speed of light for the signal. And it's easier to do time synchronization in wireless than wired, because in wired, the routers, if there are many routers in between, they can introduce a lot of non-deterministic delays for the NTP synchronization. That kind of messes things up. But recently there has been a lot of work to attack that by several other means. I think there was another paper that makes use of some packages that they inject to figure out the package delay latencies that can be added, and ignore the over delayed NTP synchronization timestamps or attempts, and they showed very good results from that as well. Okay, that was a tangent. Yep, so what's the benefit, where does the benefit come from? The benefit comes from that if epsilon is long, the clients need to wait for the epsilon to finish before they can do an update. So if the epsilon is much longer than TW, we are wasting some time. We are having spurious aborts saying that, oh, this may not have been finished. That's why it's important to keep the epsilons shorter, so we can order the events much better, because if they are epsilon is longer, we can we are not able to order, we cannot start a new one, etc. We think that they are intersecting and have to play conservatively. Okay, so this is on the Retrivis benchmark, the transaction latency versus throughput, multiversion FTL with, what was LV?
So I have a question about what you just mentioned. So you said we need to wait if the epsilon is longer. So what process is not clear to me? Like, what process needs to wait? Is it the server during the validation phase, or like, or the client?
Logically, it should be something that validates the transaction. So if it's a transaction with writes, it should be the primaries.
So it says here the lagging client has to wait for a duration greater than epsilon.
It should be.
What was that?
Not at the primaries and clients, I guess. I'm trying to figure out this part. So we can go to the paper to check this. I'm pretty much done, so let me finish.
Okay.
Slide
discussion.
Let's do this in the discussion. I forgot what LV was for. Does anyone remember? Without LV, what is LV?
It is local validation.
Oh. Oh, got it. Okay, yeah, yeah. And yeah, so they say that with LV, you get a lot more improvements for read-heavy transactions, of course. Okay, they also compare with sentiment, but this part was, I don't know. How they performed these experiments was not clear to me. They say that, oh, sentiment did not use replication and we also did not use replication. So it may be that they did this with just primaries and not even secondary replication. So I don't know what to make of this comparison or this evaluation then. So yeah, the evaluation section, I would have been happier if there were more explanation provided about this. But so that's the paper, and we can do the discussion. Hold on.